Hi. So we're back with the Engineering 20 review session. And I did get some suggestions from one student on what they wanted me to cover. Thank you, Ursula. But I have to say that basically you're asking me to cover everything. So I'll do the best I can. I'm going to start with second order circuits. And then I'm going to go and just review quickly the first order circuits. Then I'll do a source transformation. And then a phasor problem. And hopefully that's chapter 10. Hopefully that will be enough for a good review. Okay, so the procedure, the general procedure for a second order circuit. And how do we know we have a second order circuit? It's when there are two irreducible energy storage elements in the circuit. So you might have two capacitors, you might have two inductors, you might have one capacitor and one inductor. But the idea is that, that you can't reduce it down to just one energy storage element. So if you have a circuit that meets that definition, the first thing you should ask yourself is this. Is it a standard source-free RLC circuit? So what that means is do you have a resistor, an inductor, and a capacitor in parallel, or a resistor, an inductor, or a capacitor in series without anything driving it? Like you might have some initial voltages or currents going through some of this stuff, but there's no driver, there's no voltage or current source. So it might not look just like this exactly, but given a switch and looking at it after t equals 0, if it reduces to either one of these standard circuits, then there's no need to find the differential equation. Okay? So in that special case, your work is actually a lot easier. And all you have to do is calculate alpha and omega. Alpha, if it's in the case of the, I can't remember which goes with which, but the parallel and the series are a little bit different in the calculation for alpha. But anyway, you just calculate alpha depending on the values of R, L, and C. You calculate this parameter called omega 0, which is the same in both the series and the parallel cases. And then you compare the two values. If alpha is bigger than omega 0, you have what's called the overdamped case, and boom, there is the natural part of your solution. If alpha equals omega, you have what's called the critically damped case, and boom, there is the natural part of your solution. So it's just these formulas here. And then lastly, if alpha is less than omega 0, it's called the underdamped case, and boom, there is your solution. Now, there was the development of, how we solved this, but I don't really hold you responsible for that mathematical development. All I want you to do is be able to do the circuits part. It's a standard, source-free RLC circuit. This is how you go about it. You calculate alpha and omega. You compare the values. Depending on the comparison, you've got 1, 2, or this third case, you're done. Well, almost done. Going back to the idea that this is source-free, we know that the natural part is really only half of the solution, right? Because for any differential equation, the complete solution is those two parts, the forced part and the natural part. I'm only talking about the natural part here. So what's the forced part? Anybody from the audience know? Source-free. It's a source-free circuit. And then the forced part is what's going to happen after a long period of time has passed. The t equals infinity, source-free, it's going to be 0. The forced part of the circuit is going to be 0. So the forced part is basically dropping out. And so that natural solution is the complete solution for the source-free RLC circuit. Okay. So, let's do the harder problem, the one where we don't have a standard, and it's not source-free. Oh, by the way, this source-free solution is also, it's going to be the natural solution even if there is a forcing function. And so if it's not source free and there is a forcing function, you can still use this to get the natural part of the solution. But then to get the forced part of the solution, unfortunately, you will have to go back and find the differential equation, because you're going to have to go and solve for the forced part using that differential equation. So the only case where you really don't need to find the differential equation is in this source-free. Or actually, I should say source-free or a constant source, because the forced part would be very easy to find. And if you don't think it would be easy to find, then I guess you'll have to email me with that question. But it would be easy. If you have a constant source for a circuit, you should be able to easily find the long-term voltage or current anywhere in that circuit. And just as a real, quick hint, because remember, for a constant source, inductors act like short circuits, capacitors act like open circuits, so you just look at the circuit in the long term with those open and short circuits operating, and you should be able to find any current or voltage anywhere in the circuit. All right, so what we're going to do is we're going to go through a problem where it's not quite that straightforward. It's not a standard circuit, and it's not source-free. So I have such a problem. I was going to put it up before we started rolling, but I can do it pretty quickly. It's relatively simple. That's the circuit. It's got a current source of 4 amps. This U of t, remember, that's a unit step forcing function. And all that means is that for the argument greater than 0, the value of U of t is 1. For the argument less than 0, it's 0. So basically what that means is that at t less than 0, this current source is 0. So it's not here. It's a short circuit. At t greater than 0, you've got these 4 amps feeding the circuit. So this is the problem. It's kind of like the same as if I had put a switch here and said that this switched closed at t equals 0. But instead of showing an actual switch, this is like the mathematical way to indicate a switch. All right, the value for the resistor here is 6 ohms. The inductor is 1 Henry. And then the capacitor here is 1/5 of a farad. Okay, and I'm going to, all right, so there's our problem. And what we want to do in this problem is find the voltage across the capacitor as a function of time for all time after 0. Okay, so that means once this current source is switched into the circuit, we want to find what the voltage across this capacitor is. And so we know that there's going to be a natural part of this solution, right? Because it's going to build up charge on this capacitor. And so the voltage is going to build until, and notice this is actually a constant source, until it gets to that forced part of the solution, which I can almost do it by inspection. Right? In the long run, if we've got 4 amps here, and we know that a capacitor acts as an open circuit, an inductor acts as a closed circuit, all these 4 amps is going through the resistor, so the voltage across that resistor, what, is 6 times 4, 24 volts. So I already know the forced part of the solution. That's what I was talking about there, that if it's a constant source, the forced part of the solution is going to be relatively simple to get. I mean, I almost did it in my head. I'm going to erase it here because I want to use the room, and we'll get to that part of the problem when we get to it. But, okay, so this is the given part of the problem. We're asked to find the voltage across the capacitor for all time greater than 0. And so because I've just labeled this as a V, I better show exactly what I mean by that on the picture. So it's that thing that I'm looking for right there. All right, so going to my process here, it's a really simple, very straightforward process. The first thing that I need to do is find the differential equation. Once I find the differential equation, I basically have to solve it. Okay, so you do have to remember that to solve a differential equation, there's two parts to any solution to a differential equation, the natural part and the forced part. So that's my next two steps. Once I find the differential equation, I have to find the natural part of the solution, then the forced part of the solution, and then you put these two things together to find the complete solution. And the idea there is that the natural part of the solution will have two arbitrary constants. Okay? These two arbitrary constants will be obtained by knowing what some boundary conditions are. But the issue is that you can't find these arbitrary constants until the end, until you put the natural part of the solution together with the forced part. Then you apply the boundary conditions to find the arbitrary constants. So let me kind of put a complete picture here. So you will come up with two arbitrary constants in the natural part of the solution, and two because it's a second order circuit. If this was a third order circuit, you'd have three arbitrary constants. And so you would need three boundary conditions. So this is the process we're going to follow, and we're cutting right now.